Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome to our podcast session, folks. Today we're diving deep into the world of deep learning, focusing on topics from intrusion detection to computer vision and natural language processing. Let's get rolling.
I'm stoked to explore all the layers and details. They're so thrilling. What's the first stop on our journey?
Well, let's kick off with computer vision. Basically, you have tasks like image classification, object detection, semantic segmentation, and even image generation. Each of these tasks pushes the envelope on how we interpret visual data.
It's like, each image is a puzzle with millions of pixels, right?
Exactly. And speaking of pixels, the content explains that each pixel is basically a number, typically encoded in RGB values ranging from 0 to 255. This numeric data becomes essential input features for models.
Yeah, I get
It's
that.
like painting with numbers.
That reminds me. When it comes to CNNs, the convolutional layers really change the game, don't they?
Absolutely, CNNs are ingenious. They use convolutional layers as filters, which slide across the input data, learning to pick up on patterns. Then the pooling layers reduce the dimensions to manage the massive number of weights. It's kind of like sifting through a treasure chest to pick out the gems.
And the idea behind using shared weights in those convolutional filters helps in reducing redundancy. Isn't that so?
Yes, exactly. When each filter applies the same weight structure across the entire image, it saves on computational cost while still capturing critical features. It's like reusing a blueprint over and over, ensuring consistency across the architecture.
Moving on from images, the content also covers natural language processing, right? How does that integrate?
Right you are. In NLP, there are tasks like text classification, sentiment analysis, search, machine translation, and text generation. The idea is to convert text into features through methods like bag of words, word embeddings, and even attention mechanisms in transformers.
Yeah.
It's super fascinating how numerical representations breathe life into text.
Speaking of bag of words, I sometimes feel it doesn't capture context very well. What do you think?
I totally hear you, but that's why methods like word embeddings, which capture semantic meaning, and then transformers with their attention mechanisms have really pushed NLP forward. They capture context far better. It's like comparing a rough sketch to a detailed portrait.
And transformers, man, they just changed everything with attention.
Exactly. Transformers convert text into features with word embeddings, positional encoding, and, of course, attention, which gauges relationships between words. It's like every word looks around and sees how it fits in the sentence. You know?
Right. Now, the discussion doesn't stop there. It also delves into recurrent neural networks like RNNs, LSTMs, and GRUs. How do these offer value?
Good point. RNNs use hidden states which store information about previous inputs to help predict the next. This sequential context is critical in language tasks like understanding a sentence. And then we have LSTMs and GRUs, which add gates to control what gets remembered or forgotten.
I do wonder, though, sometimes, Isn't it overkill to use LSTMs or GRUs when simpler RNNs might also work fine? Yeah.
I get that, but in many applications, especially where long-term dependencies matter, the added control of gates really makes a difference. It's like
that makes
upgrading
sense.
from a tricycle to a well-tuned bicycle when the terrain gets rugged.
Then there's the fascinating part about adversarial approaches such as GANs, right?
Exactly. GANs, or generative adversarial networks, are like a tug-of-war between two networks: the generator, which creates data, and the discriminator, which evaluates it. This dynamic helps in tasks ranging from drug design to media production, and even in disguising attack traffic in intrusion detection systems. It's really a dance of creativity
Very cool.
and scrutiny.
Wow, using GANs to craft digital fakes and such. Almost mind-bending, don't you think?
Totally is like watching an artist and a critic constantly challenging each other. And speaking of challenges, the system architecture often requires balancing generator creativity with discriminator accuracy, which is no small feat.
Yep, absolutely. What about autoencoders? They seem to be mentioned as tools for anomaly detection.
Correct again. Autoencoders work by compressing input data into a lower dimensional representation and then reconstructing it. The trick is that anomalies tend to have higher reconstruction
I
error.
see.
It's like teaching the network to remember the pattern, so anything that doesn't fit stands out.
And that can be powerful for intrusion detection because fraudulent data is reconstructed less accurately, right?
Exactly. If the autoencoder has been trained well on normal data, any deviation shows up as a high
That's
error.
really clever.
Imagine it as a finely tuned filter where odd bits just can't pass through unnoticed.
I'm really impressed by how deep learning can extend across different modalities, from images to text, and even anomaly detection for security applications.
Yeah, it's really like a multi-tool approach for AI. Each method, from CNNs to transformers to GANs, has a unique role, and they all rely on robust math like matrix operations to bring the magic together.
Exactly.
It's amazing how much nuance is packed into these models.
And let's not forget the role of layers and weights in all of this. It's all about finding that right balance, right?
Spot on. For example, in CNNs, convolutional layers use sliding filters with shared weights to detect patterns, which is essential to manage complexity. If you had an individual weight for every connection, the number would be astronomical. It's like,
no kidding.
a chef not reinventing the recipe every single time, but just tweaking a few spices.
And when we talk about RNNs and the likes, reiterating through sequences really empowers the network to learn context. It's almost poetic how the past influences the present.
Absolutely. The hidden state in RNNs is the unsung hero there, carrying over crucial info from previous steps. With LSTMs and GRUs, those gates refine this process by deciding exactly what to keep and what to discard. It's like maintaining a conversation where every word counts.
There's also something to be said about the progression from basic techniques to more advanced ones, like transformers. They really revolutionized NLP by offering parallel processing and eliminating the sequential bottleneck.
Yep, transformers totally changed the game. Their self-attention mechanism, which assigns varying importance to each word in a sentence, brings a whole new depth to language modeling. It's like the difference between reading a flat text and experiencing a dialogue with context embedded into every line.
One thing that sometimes puzzles me, though, is why we need both recurrent networks and transformers. Aren't transformers enough for most tasks nowadays?
That's a fair critique. While transformers have surged ahead in many NLP tasks, recurrent networks still have their place, especially where sequential processing can benefit from explicit memory retention over time. Some applications may not require the heavy model that a transformer is, so RNNs, LSTMs, or GRUs can be more efficient. It's all about choosing the right tool for the job.
Yeah, I can see that. And then there's the overarching theme of matrix math. Just mind-blowing how these models are built on it.
Totally. From convolution operations to attention layers, the backbone remains robust matrix computations. It's like the secret sauce of deep learning. Every model, no matter how sophisticated, returns to fundamentals like linear algebra.
Very true. So, in summary, we've journeyed through the realms of computer vision, NLP, RNNs, adversarial networks like GANs, and autoencoders, all showcasing how deep learning methodologies are interwoven across different applications.
Precisely. It's a vast landscape where each technique complements the other, pushing the boundaries in tasks ranging from image recognition to natural language understanding and intrusion detection.
Yeah.
And honestly, it's fascinating to see how these models translate raw data into something incredibly meaningful.
Well, this has been an intense but enlightening deep dive. I'm feeling totally inspired about how these concepts come together to drive modern AI.
Glad to hear it. Remember, whether it's pixels that form an image or words that create context, the world of deep learning is all about finding patterns and enabling intelligent decisions.
Indeed. Thanks for joining in on this exploration. All these details really highlight the power and complexity of modern AI techniques.
Absolutely. And for those curious minds out there, dig into these models, experiment a little, and you'll discover a whole world of innovation hidden in the math and architecture behind them.
Right, exactly. Until next time, keep questioning, keep exploring, and keep embracing the awesome intersection of art and science in deep learning.
See you next time, folks. Stay curious and keep pushing the limits of technology.